Hi, everybody. Thanks so much for joining us today. The Center for Petroleum and Geosystems Engineering at the University of Texas, Austin, is happy to have you with us for our Knowledge Pipeline webinar series. Today's topic is recent advances in subsurface foam applications. The Knowledge Pipeline series is put together for our alums and colleagues, emphasizing the interdisciplinary nature of the cutting-edge work done at the Center for Petroleum and Geosystems Engineering. I'm Dr. Keith Johnston, and it is my pleasure to host the webinar today. I am a professor in the Department of Chemical Engineering at the University of Texas, but in the same building with my colleagues, and I'm there often. I received my PhD in 1981 in chemical engineering at the University of Illinois and joined UT after a year at Sandia National Laboratories. I'm a member of the United States National Academy of Engineering. I conduct fundamental research combining materials chemistry, colloid and interface science, and polymer science to guide the development of applications in a wide range of fields, including drug delivery, imaging and therapy, microelectronics, energy storage, and subsurface energy production. The last 10 years with the high price of oil, I find that the subsurface has been the one that has really garnered a lot of my time, and I've really enjoyed it. Just a few housekeeping notes. We don't normally expect issues with audio, but if you should lose sound, our suggestion is that you exit the webinar, close down your browser, and then re-enter. That generally solves the problem. For those of you who registered for CEU credit, the verification link will be posted at the end of the Q&A session and will be available for 1 hour after the end of the webinar. The verification process is very brief, and we recommend that you complete it immediately following the presentation. We will have an opportunity for discussion and questions at the end of the presentations today. I'm going to be tracking questions from our audience throughout the webinar and will address them at the end of the presentation. The webinar will end within an hour's time. Now I'd like to introduce our presenters for today, Drs. Maša Prodanović and Nguyen. Maša Prodanović is an associate professor and Chevron Centennial Teaching Fellow in the Department of Petroleum and Geosystems Engineering at the University of Texas at Austin. She holds a BS in Applied Mathematics from University of Zagreb in Croatia and a PhD in Computational Applied Mathematics from Stony Brook University in New York. Prior to her current post, she held a research associate position as well as the prestigious J.T. Oden postdoctoral fellowship. I was lucky to work with her at that time. Prodanovic's research interests include multi-phase flow and image-based porous media characterization, especially applied to the heterogeneous media level set method, foams and porous media. Ferrohydrodynamics, sediment mechanics fracturing, and unconventional resources. She was awarded the SPE Faculty Innovative Teaching Award in 2014, the Interpor Procter & Gamble Award for Porous Media Research in 2014, and the NSF Career Award in 2013, and she's still spending that good money, right? I've been fortunate to know Nguyen for about 10 years and have worked with him in one of many, many projects he works on with also George Hirosaki at Rice and Lisa Biswell at Rice. Nguyen is an associate professor and J.H. Herring Centennial Professor in the Department of Petroleum and Geosystems Engineering at the University of Texas at Austin. He is the Foundation CMG Industrial Research Chair in Reservoir Engineering. He holds a Bachelor of Science in Chemical Engineering from Vietnam Tokyo Polytechnic University and a PhD in Petroleum Engineering from Delft University of Technology. His current research is focused on many areas: advanced gas and chemical EOR methods, in hydrocarbon formations with low permeability, high salinity, and high temperature. It kind of sounds like conditions from hell. Thermal and solvent-based recovery of viscous oil and oil shale, improved production of unconventional resources, and engineering of complex fluids such as foam, emulsion, polymer gel, nanoparticle dispersion for near wellbore conformance, and far-field mobility control. With his experience in chemical engineering, petroleum engineering, and a master's in business administration, you'll see goes all the way from molecules to the field. And with those introductions complete, I'm going to turn it over to Wak to get us started.
Thank you, Keith, for the great introduction. And hello and happy Friday, everyone. And it's my pleasure to share with you some of our advances in foam improved gas enhanced oil recovery. And for today, we will talk about aqueous foam, dispersion of a gas in a surfactant solution. So I thought that would be appropriate to start with the fundamentals of foam rheology in porous media. So this picture shows you a cartoon of foam flow in a porous medium, and with the white bubbles, blue brine, and gray grains. And when a bubble trend is set in motion, the lamellae separating the bubbles exert a significant amount of viscous resistance to the gas flow. And each lamella exhibits an apparent yield stress to be exceeded by a low pressure gradient to set the lamella in motion. So if you would consider foam as a pseudo phase, and then the magnitude of foam viscosity and the amount of foam that is trapped in the pore space going to be determined not only by the lamella yield stress and viscous drag, but also by the density or the population of the lamellae or the bubbles. And foam can be generated in situ in a porous medium by three well-known mechanisms. One going to be snapping off long fingers, bubble fingers, to generate bubbles. And the second one is leaving behind liquid films as gas fingers advancing downstream of the flow. And liquid films or lamellae can divide at division site in the porous medium. So all of these mechanisms can generate foam, and together with the individual film properties like yield stress and viscous drag, it determines the foam rheology. Now, we can build these fundamentals of foam properties into a commonly used definition of foam mobility in porous media. So lambda is the foam relative mobility, and it is defined as the ratio of the foam relative permeability to the apparent gas viscosity. So let's start first with the relative permeability. It is a function, of course, flowing gas saturation. However, gas saturation in foam is strongly influenced by the fraction of gas that is trapped in the pore space. So there are different ways to study or understand the dynamics of gas trapping. One way is that you can use a gas tracer that can be visualized by X-ray imaging. So I came up with this idea several years back, and this picture shows you a CT image taken at that time. It's showing you the actual CT slide image of a barrier sandstone in which foam is injected at steady state. And the red showing you mobile foam, and the blue color showing you the fraction of foam that is trapped or not moving. Or another way to study dynamic of foam trapping is that to use a pore network-based modeling approach. So like what we have been doing here at UT Austin in my collaboration with Professor Bohoff, my colleague at the Department of Petroleum Engineering. So we reconstructed a pore network using microcity. So this showing you the actual pore network from a sandstone. And we simulate or model the motion of foam films in this network. And this figure showing you the vertical cross-section of the network in which we inject foam from the bottom and produce foam from the top. So the white background in this figure showing you pore space that occupied by trapped gas, while the red area showing you the pore space occupied by flowing gas. Now, when you see from top to bottom that where the applied pressure gradient is increasing, the fraction of flowing gas is increasing when you with the pressure gradient. So that gives you an idea about the relationship between the trap gas fraction and the applied pressure gradient. But I can give you a little more quantitative analysis of this relationship. So if you would plot the flowing gas fraction versus pressure gradient as for different foam strength or different foam density. You remember I mentioned about foam density in the first slide, that how fine the texture of the foam is. And the stronger the foam, the harder to mobilize it. Also, in other words, that you need to apply higher pressure gradient to mobilize strong foam. And regardless of the bubble density, the relative permeability of foam going to decrease significantly as the trapped gas fraction is increasing. And this is a very critical rheological property of foam in porous media. Now, the second component of foam mobility is, of course, apparent gas viscosity. You remember the definition of foam mobility going to be relative permeability over the gas viscosity. So let's talk about gas viscosity here. So this figure showing you the apparent gas viscosity in foam normalized to the ordinary gas viscosity as a function of capillary number. So this expression shows you the definition of capillary number. So one way to increase the capillary number in the pore network is that to increase the foam velocity. And you can see as the velocity of the foam is increasing, the apparent viscosity of the foam is going down, suggesting that foam is a shear thinning fluid. And to the right figure, you can see the apparent viscosity of the foam is increasing with the permeability of a pore network. This is a very attractive rheological property because that if you wish to use foam to slow down gas, to reduce the gas mobility in the high permeability zone, and then the more viscosity foam has in the high permeability zone, the more successful for foam going to offer to divert injected gas from the high permeability zone into the low permeability zone. So this is a very interesting result. Now, so we can, and the principle of foam rheology has been successfully applied in the field. For example, foam has been applied to improve gas sweep efficiency for gas flooding that in which gravity override is a very significant challenge. So for example, when you inject gas into a relatively homogeneous reservoir, because of the gas density is typically lower than oil, so that's why gas is going to override, right? So it only sweeps the upper part of the reservoir. Well, another challenge in gas flooding is going to be channeling, because nature is not uniform anywhere. So high permeability is only going to take in a lot of injected gas. So if you are using foam going to slow down gas in the red zones, and divert gas into the green oil bearing zone. So that is the application of the foam principle. Now, we have at UT developed a very successful integrated foam design framework, starting from molecular scale surfactant design, going through lab testing, including foam core flood, modeling foam properties, upscaling foam process to field, and pilot design and implementation and post-foam evaluation. And we've been using this framework for several applications in the field, including the novel CO2 foam with CO2 slope surfactant. I'm going to elaborate further a little bit later in my talk. Also use foam as a mobility control agent to replace polymer in micellar flooding, and foam for fracture reservoir. Fracture sweep efficiency in fracture reservoir is a very, very problematic challenge. And foam for gas flooding, where that the amount of gas, ironically, is very limited, but gas flood is a good option. Also foam for application like pressurizing the reservoir to improve the miscibility, to bring the reservoir pressure closer to the MMP, and many other applications that because time limit, I would not be able to go through. But I can give you a very, very quick walk through a recent successful foam application in the sandstone reservoir. So this is the pilot area. It is an inverted pattern, 5 spot. And the problem with the CO2 injection for this pattern is, one, a very poor injection profile, as shown by this injection profile. You can see that almost like 86% of injected CO2 going in only 7 feet foot interval, and the lower interval remain uninjected, and also channeling and gravity override within this area. And so we did, before foam treatment, we did a tracer test to identify, to characterize the problem of the CO2, mobility control, or in other words, to identify preferential flow paths. And you can see from the red profiles of the tracer profile collected from the four green producers right here, you can see a significant early tracer breakthrough. And after the foam treatment, you can see indicated by the green profile, you can see that there's a significant delay of the tracer after the foam treatment. So what does it mean? It means the volumetric sweep have to be increased by foam. So that's shown by the delay of the tracer breakthrough. And more evidence of that based on the almost like 20,000 barrels incremental oil recovery after the foam treatment, as in the case shown in this figure. Now we took foam to the next level that involved the use of the CO2 soluble surfactant that studied back in 2008, where I had an opportunity to work with Dr. Keith Johnston right here. He taught me about CO2 soluble surfactant, and we worked together to develop a novel foam concept. And there are several advantages of CO2 soluble surfactant. One is that because the CO2 can be the surfactant can be injected in either water or in the CO2 phase, so it's going to be a very benefit for the field implementation without influencing foam performance. To do so, you have to be able to determine the solubility of surfactant in the CO2, and this is just one example, show you how much surfactant. This is just one molecule. We have a distributed molecule structure, but this is one example that we can load up to 0.3 weight% of the surfactant into the CO2, and it is increasing with the pressure. The higher the pressure, the more surfactant you can load into the CO2. The second advantage of the non-ionic CO2 soluble surfactant is that it exhibits low absorption on carbonate rock. So this is one example that is show you the absorption of non-ionic CO2 soluble surfactant compared with conventional anionic surfactant. So you can see that the absorption is increasing, right? And the more surfactant absorption, the further delay of foam propagation. And the last but not least advantage of the CO2 soluble surfactant is that if the surfactant is able to partition between brine and CO2, it can improve surfactant utilization and robustness of mobility control. Indeed. So at UT, we have a very unique capability to first determine or measure directly the surfactant partition coefficient using high pressure, high temperature visual cells, you can see right here. And this is one example of surfactant partition coefficient versus pressure. And you can see the higher pressure, just like solubility of surfactant in CO2, the higher pressure, the higher partition of surfactant in the CO2 phase. Now you can relate the surfactant partition coefficient to the foam robustness or foam propagation in the rock through core flood experiment. And this is a very traditional core flood experimental setup where you have the core holder right here. You inject foam with the surfactant in the CO2 in the water, and you measure the pressure drop along the core. And because the buildup of the pressure drop along the core is a true measure of how fast, how robust the foam is going to be. So you use it as an indicator of surfactant and foam performance. So the three figures showing you here, to the left figure, this one for the CO2, the foam that is stabilized by an anionic surfactant, I mean it's not CO2 soluble. And then to the far right, you can see that for a surfactant that is soluble in CO2 but has a very high partition coefficient. I mean, most surfactants go into the CO2. So obviously that if you look at the slope of the pressure profile, and I say earlier, the faster pressure build up, the higher robustness of the foam, right? So it means that a moderate partition of surfactant in the CO2 give you the highest foam robustness. So that's why. So the question is that is surfactant partition important on the field scale? Because what I show you just on the lab scale. So the simplest way to run a numerical simulation, foam simulation. So the results show you that you look at the vertical cross section, right? The injector to the left, the producer to the right, vertical cross section, and you inject foam. So for the CO2 insoluble surfactant, you can see the significant gravity override, and most of the foam developed near the wellbore. But you can see the highest expansion of the gravity override zone is for, again, low partition or moderate partition coefficient of surfactant in the CO2, not for the very high partition. Was very consistent with the core flood result that I show you right here. And so this figure just to show you that there exists an optimum partition coefficient at which that you can maximize the sweep efficiency. So let me close on the CO2 soluble surfactant concept by showing you very quickly how we implemented this design, the novel form process in the field. So again, we did it for 4 patterns, but I only show you 1 pattern. And again, it is an inverted pattern, 1 injector, 4 producer. And this figure showing you the top curve showing you the baseline where showing you the CO2 injection versus time. And the second, I believe the red one showing you the CO2 injection rate during the first CO2 cycle. And then the third one is the CO2 injection rate for the second CO2 cycle. So I repeat, the black one showing you the baseline, no surfactant. The second one, the red one, showing you the first CO2 cycle with dissolved surfactant in CO2. And the third one is the second cycle with the dissolved surfactant in it. And you can see clearly that with surfactant, the CO2 injectivity is going to be lost at the early time, which indicates a significant form development near the wellbore. However, in time, the injectivity of CO2 is building up, indicating the foam is already propagated far away from the sand phase. However, if you look at the second cycle, injectivity of CO2 in the second surfactant CO2 cycle, you can see there's a significant delay of the injectivity buildup, which indicates the propagation of the CO2 from much deeper into the formation. And at the end of the second cycle, we did a profile log as shown in this figure. So you can see that this is the CO2 injection profile before foam treatment, and this is for water. You can see most of the CO2 and water invaded only the top structure of the reservoir. After the foam treatment, we managed to bring much more CO2 into the bottom, of the reservoir, was a significant improvement at the injection profile. And late time of the foam treatment, you can see that the oil production rate apparently increased from less than 10 barrels per day up to 40 barrels per day. And so very much of that is what I would like to show you for the novel CO2 soluble surfactant. And I'm looking forward to the next webinar opportunity to share with you some new developments on new additional foam pilots that I'm currently, participating in some advances in foam modeling process upscaling. And last but not least, we are working on a novel concept of non-aqueous foam for both EOR and hydraulic fracturing. And I would like to take this opportunity to thank you, my team at UT, my graduate student, Dr. Keith Johnston, Dr. Joseph Rasaki from Rice, and my other colleagues that have been supporting this development. And I've been taking you so far into the field, so I think it's time to bring you back to near the wellbore, where where Dr. Maša, my colleague, is going to share with you more about the foam application for new wellbore hydraulic fracturing. Maša.
Well, hello everybody. I will take this cue to the non-aqueous foams and see our newest developments that go in that direction. They're not completely non-aqueous, but they're something that we call ultra-dry foams. And we're trying to reduce water use in hydraulic fracturing. Keith Johnston today is wearing 2 hats. He's both moderator and he will be presenter. So I will start and Keith will continue. So we will share this presentation. So let's just start. Our goal is to establish a novel fracturing fluid technology to reduce water consumption. And how do we get there? Well, one idea is our objective is to develop high quality. By quality, I mean the volume of gas divided by the total volume. And if I have high quality foam, I'm reducing water naturally. However, the problem with such foam is that it's not necessarily stable. So how do we introduce stability? If you look at this schematic that is kind of putting things into the field application, we will have synergy of surfactants, polymers, and nanoparticles. Maybe, maybe not. Some of the foams have all 3. Some have only surfactants, as we will see in our multi-generational development of foams. And this synergy basically reduces the drainage rate and basically collapse of lamella between different bubbles and makes the foam stable. Now this foam also has to, of course, be able to, if we are going to use it for fracturing as opposed to EOR, it has to be able to carry sand once you're actually trying to fracture and develop multiple stages, especially in unconventionals. So basically our drivers is that hydraulic fracturing is essential technology for current and future hydrocarbon production, and it requires dense well spacing and many fracturing stages per well, which increases use of water. Standard base fluids for hydraulic fracturing are basically based on water, so that can introduce competition for water in arid regions. And also there's a lot of flowback water that has to be disposed. So regardless of the region you're in, there's a problem of water disposal. And also the extra use of additives that reduce leak off of the water into the formation basically can impede production later on. So our success metric here is to improve on the current situation that is basically you either use water or you use at least 20 to 30% of water in a fracturing fluid. So we would like to reduce that. So we are not necessarily going to reduce the amount of fluid that is used in the overall, which this schematic attempts to show. So basically this is injected volume normalized by the fracture volume produced. If you have just water, of course, your total fluid is water. What we are trying to get to is in this high gas fraction or high quality foams is to basically reduce the amount of water that you have in the total injected fluid. So we are trying to use less water. Of course, we're not necessarily reducing the total amount of fluid used. So our first generation or our first finding are ultra dry foams with a synergy of nanoparticles, which I'm going to refer to as NPs, surfactant and polymer. We did achieve stability of very high gas quality foams, basically 90 to 98% of CO2 by volume. And we are producing high viscosity of foams, basically on the order of 100 centipoise and up. And right now in the lab, we're seeing long lifetime hours. They're stabilized again with the mixture, this first generation of silica nanoparticles, LAPB surfactant, and HPAM polymer. We actually see them stable at conditions, high salinity conditions of 2% KCl and also high temperatures. Actually, we are nowadays pushing to even 120 degrees. So therefore, since we are still seeing them in the lab as stable, there is a potential that they will be stable in the applications in the field. And should you need to know more, there is publication on the topic. So just before I move on to characterizing these foams, here's the apparatus we use for both foam generation and the measurements. So essentially we introduce the fluids, CO2 and water through the glass bead pack. Here it says 23 Darcy, but of course this is something that is easily changed. And after the foam is produced, we look at it in the microscopy cell to basically check the texture. And after that, we measure the rheology of the foam. So basically, we use standard capillary viscosimeter. So apparent viscosity that we report in the slides from now on is based on Hagen-Poiseuille equation. And we have one more view cell that basically checks the quality and texture of the foam, that we actually have foam, so we can claim it is stable. So here are some example measurements. So one, of course, wants to tune the viscosity of the fluid, and that is done by the amount of polymer. So you can actually see in these two top figures what happens as you keep the surfactant and nanoparticle amount constant, but you basically introduce, the more polymer you introduce, the more viscous the foam, and you can actually see the range. We can go from anywhere between 10 to 200 centipoise. There's a bit of a peak around quality of 0.9 in, and this is something typical that we observe. Around 90% quality, we see peak in the viscosity observed, and then it falls down. We don't go to one, the measurements are ever so slightly hard to evaluate, so we don't know whether it's 98 or 99% here because of the very low gas saturation. Now, to look at what nanoparticles add to this mix is basically, you can see the difference between red and green curve. So we're keeping the same amount of polymer and we're keeping the same amount of surfactant, but with the addition of nanoparticles, you're gonna increase the viscosity. Same happens at a slightly different amount of polymer. Of course, you're gonna see more viscous foams. And this is something that is basically kept, keep in mind that this is log scale. If we actually now test this over different shear rates, we're gonna see always that with the addition of nanoparticles, which is the red curve, we see increase in viscosity. So if one is actually wondering what is the mechanism involved in the process, we can look at the example micrographs, and you can see that basically with the increase or the use, this is with and without silica nanoparticles, everything else kept the same. So basically you will decrease the bubble size and you will increase the foam stability. The lining of the nanoparticles in lamella will increase the stability against oswald ripening. And we actually see nanoparticles as irreversibly adsorbed to the interface, which creates a bit of an elastic interface and also prevents lamella merging. Now, we haven't tested this in the field, but we are wondering, okay, so we have these stable foams. Are they still stable in the presence of sand? And we use a sapphire cell for this. This is a 90% quality foam that has the synergy of all of the surfactants, polymer, and nanoparticles. And it was, the sapphire cell was a 2000 psi, and when we introduced, right after the foam is generated and we introduce nanoparticles, we literally flip the sapphire cell over and see what happens, and essentially even one day later the sand stops moving really quickly, and even one day later it stays there stable. So basically the proppant grains will not affect this foam stability as far as we can see in the lab right now. So basically, just to recap, we see foams that are stable, and the high continuous phase, even at very low water fractions, are produced as a result of opposite charges between surfactants and polymers. And we will see at these temperatures that basically the CO2 brine IFT, or interfacial tension, is reduced, which allows for creation of the foam at such low water fraction to begin with. And we see, because of the synergy of the three, we see low lamella drainage rates and low coalescence of foam bubbles. We have relatively small bubble size, and therefore we can produce, as a result, a very high viscosity foam, but this is something that is tunable, and it's high viscosity even at high qualities and high shear rates. The addition of nanoparticles acts as to increase viscosity and stability of the foam. So with that, I'm going to let Keith continue with our second generation foams.
So, thank you, Maša. So in those foams, we use nanoparticles. And so a question that's intrigued us for some time. And let me please switch to that camera. So I'm going to go on this. Thank you. And so what we found is that nanoparticles have the ability to stabilize interfaces, and we wanted to compare them with surfactant-only systems to see the implications. And we have the same goals with surfactants, as Maša explained, for long lifetimes, high viscosities, high qualities. So I'd like to talk about one study that we've done recently. Now, we first used sodium lauryl ethoxylated surfactant, SLES, And when we did that, we published that last year, and just in the interest of time, instead of talking about that system, I'd like to focus just on the second system. This is the work of Shihab Alzobaidi, a PhD student, along with Chang Da, in working with Maša and I, where we've used zwitterionic surfactants. They're imidopropyl carbobetanes, and they've been very effective in making these very viscous foams. So let me say just a few things about the theory. And the idea here is that when we have two films of CO2 and they're separated by an aqueous brine lamellae, we need a disjoining pressure to keep those films apart, which is shown here versus the separation distance. And what's important is to have steric and electrostatic repulsion to overcome van der Waals forces. And there could even be structural kinds of repulsive forces as well. So the surfactants provide these steric effects, but there's a challenge for these very low water foams. And that is that in this case, the capillary pressure becomes enormous. Now the capillary pressure depends on the curvature of these bubbles. They're on the order of about 100 microns. So in the plateau borders, on the convex side of an interface, of course, the pressure is lower than it would be on the concave side. So we have this driving force for drainage of these films from the center to the plateau borders. And that velocity depends on a film pressure, which depends on how this capillary pressure dependence of that parameter versus the disjoining pressure. So here's our challenge. Capillary pressures depend on the interfacial tension, the radius of these bubbles, and 1 minus the volume fraction of CO2. And we want ultra-dry films. We want 99%, 98, 97%. So capillary pressures become large. So we need to have slow drainage. It takes high viscosities in this aqueous phase because the drainage rate depends on the film thickness squared, the viscosity, the radius of these droplets, and this driving force, which is quite high. So the idea in this work is to form very viscous aqueous phases. And these viscous aqueous phases are formed with entangled worm-like micelles. These worm-like micelles are shown in a study from France, from Fémaux et al., where they showed that they can cause jamming of these liquid films. This is an air foam, an air and water foam, to prevent the drainage. So our interest was taking this idea, which they did with cat anionic micelles, and extending this concept over to CO2 water foams. And what's important here is the packing parameter. The interest here is in forming these long rods of these worm-like micelles. So this requires changing the curvature away from simple spherical micellar geometries. So to do this, to have a less curved interface, we adjust the packing parameter, which is the volume of the interface per length of the tail length, relative to the area of the head group of the surfactant. And so what we'd like to have is long tails and small heads to form these rods instead of spheres. And we do this simply by adjusting the tail length with a series of C18, C22, and C12, C14. That is cocoa, oleal, and also aerosol imidopropyl betanes. And these are zwitterionic surfactants. Now, in this case, there's advantages of having the zwitterionic head group, because the zwitterions will repel each other less than ionic head groups. So that's good. That gives us smaller tails, these smaller heads that we wanted. But we also use longer tails. So with a combination of the small heads and the longer tails, this is what enables us to have these worm-like micelles. And the worm-like micelles then viscify the aqueous phase. And by viscifying the aqueous phase, it viscifies the foam. So these are apparent viscosities measured as you showed for the earlier systems versus foam quality. And we did this for a series of salinities at 90 degrees Celsius. So these work at high temperatures, and at all salinities from deionized water to API brine, which is 8% sodium chloride and 2% calcium chloride, this forms very viscous foams even at 98% foam qualities. We found that even at 120 Celsius, these are relatively viscous foams. And so these cationic surfactants are stable. They raise foam viscosities because they allow for small bubble sizes. and low interfacial tensions, and it's the very viscous external phases that allow us to achieve these high viscosities. We've looked at pH effects. What's really nice about these zwitterionic head groups is they're pH independent, salt independent, so these can be used over wide ranges of conditions for C18 and C22 tails. And this shows an example, even at shear rates of 100 inverse seconds, which is quite realistic of what one would like for fracture fluids. These foams still are quite viscous. We actually look at the textures versus time to check the stabilities of these foams. And what we find here is that the short tails that don't form worm-like micelles lead to foams that grow quite rapidly, whereas the ones with the longer tails grow much more slowly. So as we expected, it stabilizes those lamellar films and maintains these high viscosities for longer periods of time. So the key finding from the surfactant-based studies is that with just a single zwitterionic surfactant, we don't need cationic and anionic together, we just combine them into a single zwitterionic surfactant with either C18 or C22 tails. They form worm-like micelles at 1% concentrations. Now that's really attractive. Some of our earlier work required 4% surfactant. So here we can use these at low concentrations and they're salt and pH tolerant. It leads to high viscosities at shear rates of 200 inverse seconds, even for these very ultra dry foams. The high aqueous phase viscosities and the small bubble sizes together lead to the high apparent foam viscosities. So they're stable from hours to days. We reduced a mechanism called Oswald ripening by a factor of 30 by forming these micelles. And the slow drainage rates, the viscoelastic phases keep the thick films that prevent these foams from breaking down, and they maintain thick lamellae that leads to slow CO2 diffusion and slow Oswald ripening. So I'm going to turn it over to Maša for some concluding thoughts, because after all, she is a petroleum engineer and I'm only a chemical engineer. And then after that, we'll go to questions.
Well, just to summarize, we have successfully created and characterized ultra-dry viscous foams that are stable at high temperatures, salinity, and pressures that one would like to have in field applications. They can carry propellant and could significantly reduce water use, and we are actually now looking into environmentally friendly surfactants possible. All of the results presented are actually CO2 foams, but for those of you who prefer nitro beer in your local brewery, we are actually retesting, and so far we see comparable results for nitrogen foams as well. Now, we haven't presented much on the foam behavior in fracture and leak off. We have a very basic numerical assessment, and so far, as one would expect, as long as you can ensure stability of these foams in the field, larger viscosity foams will create wider fractures and shorter half-length. And the fact that they're ultra dry will mean that there will be less leak off and less cleanup once the production starts. So I would just like you to take this image with you, basically with energized fluids or high quality foams currently in use that typically have 40 to 60% quality. We're pushing things to ultra dry foam. This is a new system from the stability viewpoint and also the amount of fluids, the relative amount of fluids used. So of course its behavior in the field is somewhat unknown, as well as its mobility both in fractures and neighboring matrix. So this is the part of the future work, figuring out what do these foams do actually in porous media, whether it's fractured or not. We also need them, we see them as fairly stable during a relatively slow single drop in pressure, but pumping them in the field will pose multiple different shear rates that foam goes through. So of course one is wondering what is happening with the stability and texture of those foams during the pumping. We are hypothesizing that we actually we will have to have tunability, so we will sometimes have to use nanoparticles for stability, sometimes not. SLES should allow triggering destabilization after propellant placement, which should allow for an easier cleanup after propellant is placed. So with that, I thank everybody. This, of course, is the work of multiple of the entire research group over a long time. So I would like to thank all of the participants, both faculty, postdocs, graduated students, and those students that are on their way to graduation, as well as our DOE and Welch Foundation funding.
Okay, well, I've noticed that when you came here from Croatia, all of a sudden we got all these new microbreweries in Austin.
Oh, yeah, that was me, yeah, right.
And so we're going to take a tour, and we're going to study the CO2 versus the nitrogen process for beers and see if that helps us for our research.
There's actually a joke here. Nobody on the project is a big beer drinker, so we kind of discovered these nitro beer and CO2 foam beers after we actually studied them in lab extensively.
Well, maybe if we become better beer drinkers,
maybe
we'll also,
improve that industry as well.
Okay, so we have some questions called in on the chat. And so Pinaki Ghosh has asked, and this is for WAC, and is the pore volume shown on tracer test results, is that the total pore volumes or the aqueous pore volumes for the tracer?
See, I'm good on the question.
Quickly go back.
Yeah, quickly go back. So this block process days, not produced or injected pore volumes. So the tracer was injected into the injector, the red one right here, and then the tracer concentration at the 4 producers were monitored, analyzed, and plotted versus days. So the idea here is that the earlier tracer breakthrough, the stronger evidence of preferential flow path between the injector and the producer. And that tracer was done during the CO2 cycle. So in the field, a typical CO2 injection strategy with water is that CO2 alternating water injection. So normally the tracer should be done, if it is a tracer, a gaseous tracer, and this should be injected in the CO2, and this is going to be, injected throughout at the beginning and continue, monitoring the tracer throughout the CO2 cycle.
Okay.
I hope that they answered your question.
Okay, let's, I think that answers it. Let's go to the next question, and this would be to Maša and I from El Sayed Abdel Fattah. Is your silica hydrophilic or hydrophobic? Does it have any surface treatment? Do you disperse the nanoparticle in CO2?
So right now, those are just plain silica nanoparticles. They have no surface treatments. Introducing surface treatments would be sort of a second step, because that would add the 4th parameter into the whole, basically hydrophobicity versus hydrophilicity.
Okay, and I'd like to add to that. One of the interesting aspects of this whole field is that there are a number of very interesting papers in petroleum engineering literature in the last primarily about 10 years on using nanoparticles in a variety of EOR scenarios. What one finds is that usually the papers don't tell what the surface treatment is because it's proprietary. And it has a profound effect on the nature of how the nanoparticles absorb at the interface, both the kinetics of how they go to the interface, the thermodynamics of how they absorb, how they affect the surface tension reduction at the interface, how they affect foam stability, how compatible they are with polymers as secondary agents, how compatible they are with surfactants. My background is on the nanotechnology colloid side, so I benefit enormously from my petroleum engineering partners that help with all these aspects of what's needed for foam properties for success in porous media. And in Europe, the nano community on fundamental foams and the petroleum engineers have these wonderful conferences, and George Hirosaki and Bill Roston and us have had a lot to do with that. In the United States, it's real strange. The communities are almost completely separate from each other. together, and I'm sort of in no man's land, you know, and I'm having a lot of fun.
Really well. It's
you know, seeing what both sides have to offer and trying to figure out how to help put them together. But I think what I'd like to say on this is that, to the extent that researchers are able to say what they have on the surface, think about surfactants. If you said, I have a surfactant that I'm going to use for EOR or foams, but I'm not going to tell you what the heads are and the tails are, all you know is there's a surfactant there, but you don't really know much about what it does, and as you know, it's very sensitive. The same thing's kind of true for nanoparticles, so I think the whole field will advance a lot more. We had a paper in Soft Matter last year where we identified very clearly some of the ligands on the surface and how that affected how well they take high temperature conditions and high salinity conditions. And so I think it's really exciting to think about large-scale applications happening in petroleum engineering with nanoparticles, and I think that gives us huge body of research for then nanotechnologists to try and figure out how they can improve upon those particles. And the companies are doing it. The companies that are providing those particles are already doing this really outstanding surface chemistry, but unfortunately, as we read these papers, usually they're not allowed to say what is on the surface. I don't know if we are set up for follow-up questions, or should I just see if they come in on the chat and then just keep going down the list? Okay, so please don't hesitate to follow up. We have one from Young Man Kim. Are your surfactants commercially available? And let's start with WAC, and then we'll go to the ones we talked about.
Yes, the short answer is yes, the surfactant is now commercially available.
One of the comments I could add to that is WAC and I published a series of papers together with support from the Dow Chemical Company, and it described a large number of non-ionic surfactants, probably about 20 or 30, right, and both interfacial properties and some of their flow through sand packs and so forth. On our side, all of the ones that we've shown today are commercially available. The betanes I showed are available. The SLES is very common. And so there's large numbers to choose from here.
And the details are available in the publication.
And yeah, they're all described in the publications in detail. That's right. The most recent publication was February of 2017.
And feel free to email us or contact us for the publication or any further detailed information of the surfactant and so on.
Just to connect this question and the previous one, part of the attempt to use silica nanoparticles without functionalization is also to make it cheaper to potentially use in the lab, and also just to have something that is easy, like silica nanoparticles is something that is really easily available. If it's going to stop the drainage of lamella, well, that's what we need.
If you could keep if you could use low molecular weight ligands with inexpensive chemistries on silating agents, that helps a lot with cost. Versus if you go to higher molecular weight ligands, that just tends to raise the price. And so, and obviously, the companies that develop these nanoparticles are very, very, aware of these conditions. And so, I think they're making some very, very effective nanoparticles for these applications. And I think if independent studies where the chemistries are known are combined with those commercial particles, then one can sort of figure out the science behind this will evolve over the next decade that we've seen happen in surfactants for many decades. Okay, we have another question by Pinnaky Ghosh. Any work done on the tolerance of the promising zwitterionic surfactants towards crude oil for foam applications, and also any possibility of wettability alteration?
If I can, answer that. So, first of all, the use of zwitterionic surfactant for foam plus wettability alteration. We've been working with several chemical vendors testing different molecule structure. First for foam, and yes, I would say that like B10 surfactant that Dr. Keith Johnston, mentioned earlier, those are very strong foam over the wide range of concentration, and especially it has a very high temperature tolerance, up to almost like above 100 Celsius degree. And recently we tested some B10 surfactant surfactant in combination with other surfactant that can alter the wettability of the dolomite and carbonate rocks. And we observed some very promising results, even though that I have to say that the absorption of the B10 surfactant in some specific rock, depending on the mineralogy, the clay composition of the rock, that it varies a lot. Some carbonate that has low clay content, I would say that the absorption tend to be lower, but it has a higher clay content. The absorption of B10 in sweat iron is surfactant to be higher. So I would be very happy to share with you some more detail about the wettability test and the foam test at 120 to 180 Celsius degree for a wide variety of reservoir rocks. Feel free to contact us.
Yeah, in some ways, the Zwitter ionics offer more possibilities than ionic. For instance, if on calcite, because, for example, in CO2 cases where calcite's positively charged, anionic surfactants don't work, and Zwitter ionics do. But then, as Locke explained, then depending on the clay amounts, then when you change the charge, then the Zwitter ionics can have more adsorption. Some cases, one might need sacrificial surfactants in these systems and combined systems. Okay, we have a question from El Sayed Abdel Fattah. Another one, does polydispersity and size of nanoparticles affect its efficiency? And it does very much, because in nanoparticles, we have a situation in which a lot of the nanoparticle is not at the interface. So if you take surfactants, supposing the surfactant's only half a nanometer long, then it blocks a lot of oil and water at the interface, or CO2 water. But when we use nanoparticles, supposing the nanoparticle is 5 nanometers, a lot of the nanoparticle is pretty far away from the interface. Then if you go to 10 nanometers, 30 nanometers, there's more and more effect here. So we published a paper with Ijung Kim and Chun Ha about a year ago where we looked at different nanoparticle sizes to look at these effects. And the smaller the nanoparticle, the better result we got, because then a greater fraction of the nanoparticle is at the actual interface versus in a sphere being further and further from the actual interface itself. So 5 nanometers could sort of be a sweet spot for these nanoparticles.
Right now, I'll just follow up. It does appear that there are simply just the presence of nanoparticles in the lamella, regardless whether they're on interface or not, simply blocks the drainage.
And nanoparticles can have wettability alteration, so there are a lot of possibilities here. Next question is from Pinaki Ghosh. Are any attempts of new surfactants being developed for applications without CO2 as the gas? So let's open this up to other gases besides CO2.
Answer is in the PowerPoint.
So the question is that without CO2 as a gas, we're talking about different types of gases.
Nitrogen, hydrocarbons, other gases besides CO2.
That's what I mentioned, that foam can be made by a dispersion of a gas into a surfactant solution. And you can use any type of gas. It can be nitrogen, can be CO2, can be hydrocarbon gas. Recently, like for example, that we are using methane or even hydrocarbon gases with a distributed carbon number for controlling the mobility, not just the hydrocarbon gas phase in the gas flooding, but also to control the liquid hydrocarbon phase, that injected one through foaming for improved volumetric sweep efficiency. Yes. So as you know, that if the selection of surfactant for different interfaces between, let's say, CO2 water or hydrocarbon water going to be different because of the polarity, because of the affinity of surfactant for CO2 would be different from affinity of surfactant for hydrocarbon. So yes, this is a very exciting topic, and I would be very happy to talk about it more. So the foam, hydrocarbon foam, nitrogen foam, and CO2 foam, and the surfactants are quite different for these foam, particularly for hydrocarbon, I would say.
And we have repeated basically CO2, give or take repeated the same stability and rheology study with nitrogen foams. And the entire series of surfactants that have been tested with CO2, we see similar results also at high temperatures, high pressures, high salinity for nitrogen foams as well. Now, those haven't, again, none of the foams that we presented on were actually tested in the field. So that's a good question of what would work better in field, CO2 or N2.
And one general rule that you may, take into account when you screen for surfactant is that interface tension between, the gas and the liquid phase. The lower interface tension is going to be a more narrow surfactant pool for you to choose to stabilize foam.
I think with that, we're going to go to the ending statement. And many thanks for attending today's webinar. We will send more information on the next webinar. As soon as the data is set, you can sign up for updates on the Knowledge Pipeline page of our website, listed on the final slide, www.cbge. If you're going to claim CEU credit, don't forget to click on the verification link on the final slide. This webinar has been recorded and available on the next CPGE website early next week. Thank you so much for joining us.
Thank you.
Thank you. Have a good weekend.